remote surveys, call detail records, administrative data, social media, and remote sensing. And that session highlighted the tremendous potential of these sources, including the promise of conducting faster, cheaper, and in some cases more rigorous impact evaluations at larger scales and in harder to reach locations. It also highlighted some key limitations and challenges, including issues related to data, like bias issues, construct validity, ground truthing issues, transparency, ethics, including privacy, security, engagement with stakeholders and beneficiaries, and so forth. And it also raised questions about the resources and capacity needed to make effective use of big data in evaluation. So this session now builds on and continues that conversation from Asian Evaluation Week last year. But this year, we're focusing more specifically on one of those key types of big data, remote sensing. So a little bit of a background, what is remote sensing and why did we choose it? In short, remote sensing is acquiring information from a distance. And this refers specifically to sensors on satellites and drones. So this does not include mobile surveys or querying administrative databases or social media platforms or the like. So why remote sensing? In 2020, 3IE completed a systematic mapping exercise of measurement studies and impact evaluations using big data to study any of the 17 Sustainable Development Goals. And one of the key takeaways from that was that satellite data was used in over 80% of the impact evaluations we found, and over 70% of the measurement studies. So that's a major source of big data for impact evaluation. So that's why we're focusing on that today, and we're digging a little bit deeper. So we're going to learn about some of the great work done by 3IE grantees using remote sensing in impact evaluation. In terms of logistics for the session, we have two 25-minute presentations, and then we will have about 25 minutes for discussion afterward. The first presentation by Dr. Yan Yan Liu focuses on the evaluation of sustainable land management of a sustainable land management project in Ethiopia. And the second presentation will be jointly delivered by Dr. Srija Jaiswal and Aniket Navalkar. And that presentation focuses on an evaluation of the socioeconomic and environmental impacts of a major transportation infrastructure investment in Western India. So I'm in a moment going to hand over to Yan Yan to deliver her presentation. But just before I do, a few words about Yan Yan. Dr. Liu is a senior research fellow in the Markets, Trade, and Institutions Division at the International Food Policy Research Institute, or IFPRI. Her research has focused on program impact evaluation, microfinance, microinsurance, and economic transformation. She received a joint PhD in economics and agricultural economics from Michigan State University in 2006. And prior to joining IFPRI in 2009, she worked for RTI International and for the Development Research Group at the World Bank. Yan Yan has conducted several impact evaluations with 3IE, including a recent study using big data to look at the impact of subway expansion on traffic congestion, air pollution, and housing prices in Beijing. Though today she will be sharing a very different evaluation that makes extensive use of remote sensing. So Yan Yan, over to you.
Hi, thank you, Doc, for a nice introduction. Let me share my screen. Hello, everyone. Good morning, good afternoon, and good evening. I'm presenting an impact evaluation study using remote sensing data in Ethiopia. This is a joint work with Susanna Constantna, Jiaming Wen, Ying Sun, and Shun Chaunabayashi. Susanna is a colleague at IFPRI with me, and Jiaming and Ying is at Cornell University. They are in the Department of Soil and Crop Sciences. Jiaming is an advanced PhD student working with Professor Ying Sun. Shun is an economist in the World Bank. Our study combines satellite imagery products and quasi-experimental impact evaluation methods to investigate the impacts of Ethiopia's sustainable land management project on land productivity. This program targets watersheds in Ethiopia's highlands. It's implemented in 3 phases. The first phase ranges from 2009 to 2013, which covers 45 watersheds. The second phase started in 2014 and ended in 2019, which covers additional 90 watersheds. The third phase just started. In this study, we are going to evaluate phase 1. There are several key components in this project. The most important component is the integrated watershed and land management, including irrigation, afforestation, pasture management, etc. The other 2 components include capacity building and land administration. This map shows the phase 1 and phase 2 locations of this project. The phase 1 locations are marked by blue, and the yellow block shows the phase 2 locations. There are 3 key innovations of this study. First, we use SAFE and EVI as land productivity measures. These are 2 complementary but different satellite imagery productivity. We use it to check the robustness of our results. Second of all, we use a SAFE-based gross primary production, SAFE GPP, to provide a quantifiable measure of land productivity. This allows us to interpret the findings in terms of both statistical and economic significance. We also investigate the program impacts on resilience to drought. This is an imperative but understudied research question. This study relies exclusively on geospatial data with public access. This allows for a very cost-effective evaluation. Our analysis unit is pixel year. We focus on main crop season ranging from June to September of each year. The outcome variables include SAFE GPP and EVI. Both are measures of land productivity. Our key control variables include rainfall and temperature, elevation and soil quality, agroecological zones, and percentage area covered by crop and by rangeland. Our identification strategy is difference in differences plus pipeline design. So we use phase 2 locations as the control group to estimate program effects of phase 1 locations. This is because phase 1 and phase 2 were selected following similar criteria. So we expect they share similar geographic and ecological conditions. We use data from 2002 to 2015. The pre-intervention period ranges for for 9 years, from 2002 to 2009. We have intervention period from 2011 to 2015. We noticed that we cannot extend the intervention period to more recent years because this is restricted by our identification method pipeline design, because in the effective start year of phase 2 is 2016. So from 2016, we don't have control group. We also use event study analysis to test parallel trends assumption underlying our identification and to show dynamics of program effects. Our event study is modeled analysis is set up like this. Here, the dependent variable is EVI of safe GPP at pixel I in AEZD in the main crop season of year T. And these dummy variables indicate year T falls into event interval N. And the T is the treatment locations. X is set of control variables, including rainfall, temperature, and their interactions with key terrain and soil quality variables. Delta I is the pixel fixed effects, and the gamma DT is AEZ year fixed effects. Here, the parameter of interest is theta n, which captures the difference in outcome variable between the treatment and the control group in event year N. The results using EVI as dependent variable is shown in this graph. Here, the horizontal axis shows the years, and the data is plotted here, shows the difference in EVI between the treatment and control locations by year after controlling fixed effects and confounding factors. And the vertical dashed line shows the start year of this program, phase 1. On the left-hand side, we can see we don't see a clear trend of those difference between the treatment and control group. However, on the right-hand side, we see that we probably are going to suggest the results probably suggest a positive effect of the program, right? We have like all of the difference is positive. And also it shows that the effect might be higher in the last 2 years. Here shows the event study result of safe GPP. We can see the similar pattern exists. On the left-hand side is flat. We don't see a clear trend. On the right-hand side, we see most of the difference are positive, and the last 2 years still we have a higher effect in later years post the intervention period. So our main results are estimated using this DID model. Here, this one post indicates post-intervention period. T is still the treatment locations. So this is the other variables are same as the event study. Here, the parameter of interest is theta, which estimates the average effects of the program during the intervention period. To look at the drought buffering effect, we define a drought indicator, which is defined as large negative deviations from normal rainfall. That is, we define the rainfall Z-score less than negative 1.5. This figure shows proportion of pixels under drought from 2002 to 2015, both the treatment group depicted in the solid line, and for the control group, which is a dashed line. So we can see 2014 and 2015 are drought years in which almost 80% of the pixels suffer from a drought. And the pre-intervention period, 2009, is also a drought year. Here, we interact this drought indicator K with post-intervention dummies and treatment dummies. And the parameter of interest is mu. Positive mu implies that the program improved resilience to drought. That is, the treatment locations would have higher land productivity than the control locations when suffering from drought during the intervention period. We find that this program has increased land productivity by 6.3% in drought-affected area. The increase is much lower at 2.1% in land productivity in no drought areas. This indicates a large drought buffering effects. We make 2 contributions. First, we provide the first empirical evidence on large effects on resilient to drought of sustainable land management projects, we also show the potential of combining remote sensing technologies with impact evaluation models to assess ecosystem restoration programs. So next I'll talk about the application. The first question is why did we use remote sensing data? That's because conventional impact evaluations relying on household surveys are not suitable for these ecosystem restoration programs. First of all, such programs often start before a baseline survey has been conducted. Second, program effects often materialize over many years, and conducting many surveys to capture dynamic program effects are very expensive. Also, it's quite difficult to include sufficient number of observations hit by natural disaster to examine resilience outcomes, because the natural disaster, the drought shock is relatively rare. So we need to increase the sample size, and as sample size increases, the survey cost will be much higher. And using remote sensing data help us to overcome some of the problems. First of all, the public available remote sensing data make impact evaluation very cost effective. Second of all, remote sensing data can date back many years before the intervention, which allows for exploration of pre-intervention trends. Third, the high spatial and temporal coverage of remote sensing data allow us to estimate dynamic program effects over a longer period. It also allows us to estimate resilience to negative shocks, which do not occur very frequently. Also, remote sensing also can provide an alternative to self-reported data, which are subject to non-classical measurement errors. And remote sensing also allows impact evaluation when on-ground data collection is difficult due to conditions such as conflicts of the current COVID pandemic. So how to process such a project? I think it's most similar to what we usually do for impact evaluation using household data. So we first need to think about what are the outcome variables and what remote sensing data are needed to measure the outcome variables. Then we need to think about what would be the suitable identification methods to establish causality. And the third step is to merge the geospatial data sets with program locations. This is the key for this type of study. We need GPS coordinated map of program locations, and we need to select analysis units. In our case, it's pixel year. Usually in conventional impact evaluation, it's household year. The size of the pixels is determined by the spatial resolution of the dependent variable. In our case, we use two spatial. Our EVI has higher spatial resolution. So our pixel is 1 kilometer, and SIF is of lower spatial resolution, and the pixel is 5 kilometer. And then we need to merge remote sensing data sets at the analysis unit level. In our case, we merge data sets through a spatial join using the centroid coordinates of that pixel grid as reference points. So after this step, we can analyze the data the same as the conventional impact evaluation. In terms of key challenges, I have been working on impact evaluation projects since 2006 for over 15 years. And actually, this impact evaluation is one of the most efficient ones. I would attribute it to our terrific research team with interdisciplinary expertise. So for this type of research, we need to know the program implementation details because that is key for identification strategy and data merging. And Shane spent a lot of time get this information to us and arranged a lot of meetings with the implementer of this program. Also, we need expertise in remote sensing and crop sciences. Jiaming and Ying are standing on the frontier of this research area, and they are very open-minded and provide valuable inputs to this study. Lastly, we need expertise in impact evaluation methods and empirical skills. My colleague Susanna is exceptionally intelligent and hardworking, and to which I'm very grateful for her inputs. And also, we know that remote sensing data are not free of measurement errors. So we need to use different remote sensing theories for robustness check to support reliability of our results. In terms of resources, first of all, a research team with interdisciplinary expertise and effective communication is key. And also we need high capacity computational support for analysis of large data, big data. Last but not least, donors support is very important. Sometimes donors tend to support impact evaluation of ongoing projects rather than projects that have ended. However, look at long-term project effects can help us better understand the benefits of the program. This is especially true for the ecosystem restoration projects in which the benefits are realized over many years. Also, it will help us understand the sustainability of program after active implementation period. So I think it's very interesting to look at after the program, the outside support has supported whether the kind of program can be sustainable. There's two key takeaways. First of all, remote sensing technologies can be successfully incorporated into impact evaluation models to allow for cost-effective impact evaluations on longer-term effects of program, and when on-ground data collection is difficult. However, I want to address that remote sensing is not to place household surveys. Instead, it's complementary to household surveys, because household surveys can be used to investigate of gender and social inclusion, can provide direct insights about well-being of household and community, and more important, can help us understand the underlying mechanisms through which the effects are materials. So remote sensing data is what we see from the sky, and we still need household survey data, the data on the ground, to understand what was actually happening. And so we conclude that impact evaluations relying on remote sensing should be complemented with on-ground, low-frequency household surveys. Thank you, that's all. I think I finished earlier.
Thank you so much. Thank you, Yan Yan. Great presentation, and I'm excited for the next one as well. I just want to say for participants, if you have questions, feel free to type them in the Q&A as we go. We will address them in the final 25 minutes. And so that's any questions you have for Yan Yan based on what you just heard, and also any questions that come up as Aniket and Srija are presenting. Feel free to type those in the Q&A. And also just a note to what to listen for. You heard in Yan Yan's presentation a little bit about her motivation for using remote sensing, like why was it necessary in her study to use remote sensing as opposed to a household survey. So she talked about that value proposition aspect. She gave some background on her study design and the results. And then she talked about the key steps of the process, some of the challenges, and resource considerations. So listen for those same 4 themes as Aniket and Srija are presenting as well, sort of the value proposition, key process steps, challenges, and resources. And if this is something that's of interest to you, either as an individual researcher or as part of an organization conducting research or funding research, think about what questions you have from a practical standpoint that you would like to ask the researchers at the end. Okay, so I will now just briefly introduce our next panelists for our next session or next presentation, which will be on the socioeconomic and environmental impacts of the Konkan Railway. Dr. Srija Jaiswal is a senior economist at the MS Swaminathan Research Foundation in Chennai, where she supports and manages the climate change program area. Her research interests include equity and justice in climate policy, climate finance, applied microeconomics, and impact evaluation of environment policies. Srija completed both her master's and PhD in development studies at the Tata Institute of Social Science, where she also worked as an assistant professor. Previously, she served in various roles, contributing to the preparation of research and policy papers for India's 3rd National Communication and their 3rd Biennial Update Report to the UN Framework Convention on Climate Change. Aniket Navalkar is a doctoral researcher at the Center for Climate and Sustainability Studies at the Tata Institute of Social Sciences in Mumbai, where his PhD research focuses on geospatial techniques in infrastructure and ecosystems resilience. His research interests include sustainability studies, impact assessment, attribution studies, remote sensing, man-animal conflicts, and the philosophy of science. And Aniket completed his Master of Science degree from the Tata Institute of Social Science in Mumbai in Habitat Studies. So over to you, Srija.
Aniket, if you could.
Yes.
Yeah.
Is the presentation visible? Yes.
Yeah, thank you. Could you go on to the first slide? Yeah. So I'll begin with giving you a brief overview of our study, and I'll summarize the results, whereas Aniket will take over and speak about the practical challenges of using remote sensing data in our study, as well as he'll guide you through the process of using remote sensing data. So we carried out an impact evaluation of the Konkan Railway. So our guiding question, so mega infrastructure projects in India as well as elsewhere have quoted significant significant controversy, especially controversy in terms of pitting environmental concerns environmental concerns against development concerns. And there has been a lot of polarized debates around in large infrastructure projects, especially when they are planned in sensitive ecological zones. One such infrastructure project was the Konkan Railway. Konkan Railway was built through the Western Ghats. The Western Ghats is a global biodiversity hotspot in the western region of India. And it is a 760-kilometer long railway line passing through the 3 states in India. It is one of the biggest infrastructure projects built of independent India. And it was identified as a contested space of environment versus development in one of the reports for the preservation and preservation of environment, preservation of Western Ghats, which was commissioned by the government of India. This was a rationale of choosing to do an impact evaluation of the Konkan Railway. We wanted to see what has been the socio-economic and environmental impact of the Konkan Railway. Next slide, please. So what did we specifically want to know? We wanted to know what has the Konkan Railway done for the population, how has it changed the demographic composition around the railway station and the villages around the railway station, and what has it done to the workforce composition? And what has it done to the land use change around the villages around the railway station? Specifically, we also wanted to know what has happened to the land use change and environment around the Konkan Railway track, as well as in the villages around the railway station. When the Konkan Railway was proposed, there was controversy regarding the damage it would cause to the environment in the Western Ghats. Therefore, we wanted to see how the line has affected the environment in the region. Next slide, please. So our methodology was to use a quasi-experimental research design using a difference in difference methodology. So we had for our unit of analysis, we had villages. Sorry, just to rewind a little bit. So we use census data in conjunction as well as remote sensing data for assessing the demographic changes and sectoral composition of the workforce. We use census data, whereas for assessing the land use changes, we use census data as well as satellite data. Our unit of analysis for the sectoral changes in workforce as well as population changes was villages. For land use changes, it was villages as well as 4x4 kilometer boxes which we drew around the railway track. So here we have a visual description of how we defined our treatment region. So on the left side, you see the Konkan Railway track. And so in the census data, from the census data, we had villages as a unit of treatment. So we drew treatment region was villages within the radius of 10 kilometers around the railway station. Whereas for the satellite data, we as you see in the image, we drew boxes of 4x4 kilometers around the railway track. And there were around 300 boxes of 4x4 kilometers on the railway track. And as a control group, we drew similarly 300 boxes of 4x4 kilometers, 10 kilometers away from the railway track, then again 20 kilometers away and 30 kilometers away. And then we carried out a difference in difference analysis with the treatment and control groups. Moving on to the next slide. So the data sources, as I mentioned, was the Census of India, as well as the satellite images. And in order to control for a number of locational factors, such as the distance of the village from the railway station, from the highway or from the coast, and elevation, we used digital elevation models as well as GIS techniques in order to control for the distance of the village from the highway and the coast. And so the rationale for using remotely sensed data was, especially for the land use change, was that the census data is based on the village records, which are not generally up to date. And the remotely sensed data is available at a greater frequency, allowing us to assess change over time. Moreover, around the railway track and stations, the land may not belong to the Indian Railways, and it might not get recorded in the village land records. Moreover, the Konkan Railway had acquired land for double tracking of for making a double track, but it eventually built only a single track. Remotely sensed data also provides a cost-effective and accurate method for a large study areas such as ours. Next slide. So what did we find out? So between 1990, just to give you a brief background of the Konkan Railway region. So the Konkan Railway passes through the eponymous region called Konkan. So the Konkan region is known for its out-migration of male workers. And it has historically had a high female to male sex ratio. That is, the number of females per 1,000 males has always been higher than the rest of India. And so what we found was the female to male sex ratio had actually gone up around the villages around the railway station, and so had the population. As on the other hand, the number of main workers, that is the number of workers who work who work more for more than 6 months year, that had gone down. So that sort of indicated that the male migration from the region had in fact actually increased. So the Konkan Railway was actually sort of fueling more out migration instead of getting more employment into the region. When the Konkan Railway was proposed, it was assumed that it would bring in more employment by generating more industries to come into the region. However, as the industrial development in the region did not pick up, we actually saw more out migration taking place. As far as the land use change was concerned, we actually found from the census data as well as from the satellite data, we found that there was forest land use showed no significant change, whereas the agricultural land use had declined, which we attributed to the increase in non-farm activities around the railway station as well as around the railway track. There was no change in water bodies, whereas the amount of open space, that is open space, which are also included in our case, built up land, had gone up, which was again due to activities around the railway station. Moving on. So the result that there was no change in forest cover was a significant result for us, given the controversy I spoke about earlier, that the Konkan Railway had generated controversy around its environmental damage. Though we cannot say conclusively that there has been no environmental damage, because we have to see other indicators of environmental damage such as habitat fragmentation. But on the parameter of land use change, that is forest land being converted into non-forest land, we found that the forest area had shown no significant change. That was one of the most important results of our study. Now, in the next half of the presentation, Aniket would guide you through the challenges and of using remote sensing data and the opportunities which arises through it. Over to you, Aniket.
Okay, thank you for giving a backdrop of the project, Srija, and listing out the main findings. Just to build over what Srija said, what gave impetus to using remotely sensed data was also the previous studies that we had referred to. And one of the main studies was by Jeremy Attack and Fred Bateman, for the American Midwest in the 19th century. And the question that was tackled in that study was that did railroads, did it induce economic growth or did it follow economic growth? And the outcome variables that were used were urbanization and population growth. So in this, they had used historical map archives from the Inter-University Consortium for Political and Social Science Research between 1719 and 1970. So basically they had used data from the 19th century, as well as travel guides from the 1840s for these various states in the American Midwest. The other study that we referred to was on the impact of rail access on the agricultural improvement of land by the same authors. They used similar data, but in addition to that, they also used a historical GIS transportation database. And we referred to a study on land use, land cover change for the Hangzhou International Airport in China by Changsheng Xiong and his colleagues. And they used satellite data, but they did not use quasi-experimental design. I mean, they used cellular automata. So the main findings of these impact evaluation studies was that in the study of urbanization, it was found that there is a small positive impact on population density and a large positive impact on urbanization due to the introduction of railroads. But the study had a limitation, and that is that GIS data was not that reliable because it was sourced from historical sources. And at that particular point of time, remotely sensed data was not available. It's the same with the other study as well. It did find that the cultivable land had increased, but reliability was a problem. The problem with the study in Xiong et al. That we found was that they used cellular automata, a CA Markov model, to simulate the counterfactual. So we do not have any understanding of, the model basically assumes that the rate at which the land cover transition takes place is constant. And there is no parallel trends assumption like in DID to be able to verify this. So also robustness checks becomes a problem here in this particular method. But what we thought is that, what if we combine DID and if we use remotely sensed data in our case, because our pre-treatment year was not that far back. So there was availability of remotely sensed data, although there was an issue with quality and also the procedure that will be used to classify the classification techniques that are used to get a very accurate output, which I'll be subsequently discussing. So the materials that we used in terms of data were, we used Landsat 4.5, the thematic mapper sensor for 1991, between 1991 and 2015. We also used IRS-1D, which uses a list sensor for the years 2003. And for ResoSat-1, which is IRS-P6, we use for 2008, and ResoSat-2 we use for 2014. All use the same sensor, and this is the cost that is associated. We had sourced the list data from the National Remote Sensing Center of the ISRO, or the Indian Space Research Organization, and we got this data. So the reason why we chose this data, list data over data from Copernicus or any other satellite, is because we could avail of an institutional discount price for the data. Other data that we used is we used controls for elevation in our DID setup too. So we used Cartosat-2 30 meters digital elevation models, and this is all open source, so you can download it right off the Bhuvan website. The other data is that we use for accuracy assessments was Google Earth and topo sheets, because Google Earth imagery before of the 1990s, during the pre-treatment year, is not very. It's a little coarse. So we use topo sheets for accuracy assessments for our pre-treatment year, for the data, the classification output of a pre-treatment year. For the software, we used AIRAS Imagine for doing most of the image processing, georeferencing, radiometric corrections, mosaicing, and also for deploying the classification, the machine learning algorithm that did the classification, as well as for accuracy assessments. We used ArcGIS for digitizing the rail and road networks, for extraction of land cover, for making the quasi-experimental design that Sricha had elaborated. And the spatial analyst toolkit of ArcGIS was particularly useful in extracting the land cover classes from specific areas from our samples, from our treatment and from our control samples, and as well as for doing change analysis. The processing of the data was done in RStudio. So RStudio was used for area enumerations, for DID analysis, for LULC change analysis. And all the software was hosted on a workstation with an 8-core processor with 32 MB of RAM and a 2 terabyte hard drive. So the outcome variables for DID were basically, we did the analysis at level 1. We wanted to go into level 2, but we faced many issues because the expanse of our study area is approximately 57,000 to 58,000 square kilometers. And we kept getting a lot of interscene differences, which I'll be talking about subsequently. So what we had to do is we had to club open spaces. We had to club the built up land as well as the barren land in open spaces. And of course, water bodies include lakes, rivers, streams, etc. A forest cover, we amalgamated the deciduous, evergreen, and mixed forest land as forest cover. And agricultural land, cropped and uncropped. For the purpose of classification, we did cropped and uncropped separately, but when we enumerated it as one agricultural land. And it includes all these land cover classes that fit within Anderson's level 1 of LULC classification. So we did the analysis in two stages. So what happened is that in the first stage, we were just waiting for procuring all the data. So we decided to go ahead with Landsat data, thematic matter, enhanced thematic mapper, as well as Landsat OLI. And we used controls only for one. So we used only one control region, which is at 10 kilometers away. So here we can see this is the railway line. These are the boxes from where we extracted our samples. This is the control region. This is the virtual line. Okay. The list, and we also wanted to use multiple data, multispectral data from multiple sources, and see whether we get similar results. So here, of course, we had to these gaps that you see are where we couldn't, where we were still in the process of procuring the data, and when we put it through supervised classification, and then we extracted and we conducted the DID. Of course, the DID uses the standard setup. So we have one treatment dummy, and we have a time period dummy, and we have the interaction term, which is the DID estimator. So I'm not listing out all the formulae, but we did see that we get similar results in terms of the change in land use. I mean, in terms of the treatment effect. So these are not very different, although the samples, the number of observations for the t-test are different for Landsat and for LIS, and they are sourced from different satellites. So that kind of gave us confidence. But again, we had issues with accuracy. We were not getting good results for accuracy. So we decided to change our quasi-experimental design. And we also wanted to take care of other things like selection bias, etc. So that's where we decided to extend our region of analysis. So in the sense, we extended our quasi-experimental setup to include more controlled regions and see if we are getting the same kind of an effect with multiple control regions. Then what we also did is we used the rule-based classification. So we used hybrid classification, which combines the unsupervised and the supervised methods of classification. And we included more years post-treatment. So we wanted to observe if there are any incremental effects of treatment. And for that, we, in order to understand whether rule-based classification actually suffices our purpose or not, whether it meets our challenges that we have faced or in accuracy or not, we refer to some studies. And in a study for Acadian wetlands, it was found that hybrid classification indeed does give better accuracy over unsupervised and supervised methods. And similarly, there are various theoretical as well as empirical arguments that are in favor of using a hybrid classification approach. So this is the workflow that we used for deploying the hybrid classification method. One of the challenges that we faced in our in preparing the data set was that since the data is not available on, so the tiles are not available at the same time, in the same light conditions, etc. So reducing the interscene differences while mosaicing was a little bit of a problem, and we had to try different techniques like histogram equalization, histogram matching, etc. While mosaicing. The second problem was that some of this data, especially the one from IRS 1D, it's not orthorectified. So we had to use the Cartosat DEM and orthorectify the data. And after finally preparing the data set, we designated a few sample areas from which we clipped the data, and we took it through the process of unsupervised classification. Then based on what we got as our unsupervised output, we compared it to the reference images. We tested for spectral class separation. And if we got a good, so we used various tests like to measure the spectral distance, like Jeffrey's Matastuta tests, etc. If we did find a good separation, we went ahead and created the signature files for supervised classification. And for supervised classification part, we use the maximum likelihood algorithm. The classified LULC outputs were then put through accuracy assessment tests. For which we use the standard confusion matrix along with the kappa tests or the CART statistics. And we did find that, for two data sets, I'm just demonstrating the results, we did find a change in the accuracy from supervised to hybrid when we changed the method. So we did see that there's a quantum jump, especially for the 1991 data set, which is a slightly older 30 meters data set from the Landsat thematic mapper, because we couldn't find LIS. We have LIS1, but LIS1 has a very coarse resolution, so we decided not to use LIS1. We did see that open spaces, the kappa statistics show that the accuracy has improved. Even the overall classification accuracy had increased. It's the same with the 2014 data set. So one sense that we are getting is for older data sets, rule-based classification methods can definitely yield yield better accuracy. Post-classification analysis, again, here we imported the outputs into the ArcGIS environment, used spatial analysis. Then we imported the outputs from the spatial analysis into the R environment. We carried out the baseline tabulations of the DID estimations with and without elevations. So the elevations were extracted as median elevations from the boxes using the Cartosat DEM. And we created the LULC tables for each year. And again, we imported those tables to merge with the maps. For change detection, we used a certain algorithm where we used not the natural pixels, but we divided the entire area into 1 by 1 square kilometer pixels, and we did a pixel by pixel mapping. So we developed an algorithm to assist with that. And then we got the change maps as well. And this is what the change maps look like. And we can also see in this in these change maps that the interscene differences not being resolved have given some of these edges. So these we were not able to get rid of. Although, these images still help us in understanding the trends in land cover change around the railway as well as the highway. So what were the challenges? So the challenges, were that availability and quality of archived data is a problem. So we would have loved to test the parallel trends at assumption with older data, but the older the data, the quality becomes a problem. And also, to find a substitute for remotely sensed data, especially in a country like India, where data and land surveys, etc., are not easily available and they're not well archived, that again becomes a challenge. So if you want to use remotely sensed data with other data from survey, if you want to integrate both types of data, that is very challenging. Again, with medium resolution data, so which 30 meters with 23.5 meters, level 2 and level 3 classification becomes a problem. So as Srija talked about the quality of forests, the fragmentation of forests, this is only possible with level 2 and level 3 data. The challenges increase when your area of coverage is large. So for a smaller area, you can still do a level 2 classification with only a few scenes from medium resolution data. And so level 1 accuracy issues, again, with cropped and uncropped, they persist. So we got very low accuracy for cropped agricultural area. Hybrid classification, we were not sufficiently able to improve on the accuracy, although the overall accuracy improved, especially with open spaces. Cropped agricultural area, we were not able to sufficiently improve our accuracy. So there have to be other techniques that need to be incorporated, like ground truthing, etc. Because so that needs to be considered while accuracy assessments. Second thing is that there is a lot of spectral confusion between open space and built up LULC type. So if you take up a confusion matrix or you do any of the spectral separation tests, you'll find this. So that's the reason why we had to club these together. We didn't use vegetation indices. So the one that Yan Yan talked about, enhanced vegetation index, or there are other vegetation indices like soil adjusted vegetation index, or total vegetation index that also takes into consideration the land surface temperature. These need to also be used for these kind of experiments. Accuracy assessments, again, difficult with historical data, because the older the data, the less reliable it is. Resolving interscene differences because of different time periods of the scenes, that becomes a problem. And the second question is, what images to use. I mean, when you're doing a multi-temporal analysis, we are doing a multi-temporal analysis across resolutions as well. So the spectral resolution that was available back then is different from what's available now. So should we just suffice with an analysis with AWIFS and MODIS? Do we use LIS and Landsat? Do we get into hyperspectral imagery as well? But then how do we do a temporal analysis if we have data across resolutions? Computational problems were with proprietary software, and basically all the image and the data processing operations could not be integrated on a single platform. So right now what is happening is that geocomputational techniques are being developed in open source, particularly on the R and the Python platforms. But even then, they are not as robust as in proprietary software. These softwares are again not platform independent. AirDust Imagine uses an external key. So if that key gets lost, then it's not possible to run the software, which had indeed happened in our case. So again, interoperability changes, migrating data from one platform to the other. Some of these software are only supported on the 32-bit, which makes it very computationally intensive, because it cannot use the full potential of the available memory on the hardware. So what are the possibilities of overcoming limitations? Again, open source GIS software is more integrable, it's more interoperable with programming platforms like R and Python. As far as so we did an overall study, but I believe that micro level studies on impact evaluation also need to be done. So we need to do studies at the level of village or districts and see what's going on in terms of land use change at that particular level. And for that, we need to use high resolution satellite data. More ground truthing studies are again required for better accuracy assessments. But then the problem here is, when you have such a huge area, there are manpower considerations for doing accuracy assessments. So we had also purchased GPS for the purpose of accuracy assessments, but the problem was with manpower, really. And then, of course, level 2 data, using level 2 data and vegetation indices, it's desirable for impact evaluation. And for historical data, there are emerging techniques in machine learning and deep learning tools, which will help in a more accurate reconstruction of historical land cover. So these need to be studied, and these need to be developed further. The key takeaways of this entire endeavor in terms of using remotely sensed data is that definitely remotely sensed data reduces the uncertainty in impact assessment outcomes. There is no doubt about it. But the key to this, to use remotely sensed data effectively, especially over a larger area, is that you need to use good image processing technology. And the one that I found on the Erdas Imagine platform is unfortunately not sufficient. There are more advanced softwares also, but obviously they're more expensive. And the use of reliable reference data, Google Earth images, topo sheets, is very important to put remotely sensed data to an efficient use. Ground truthing improves the quality and efficiency of procedures that use remotely sensed data. And unfortunately, we were not able to use ground truthing in this endeavor. And newer techniques in machine learning and deep learning can help enhance the quality of historical data. So these are our learnings with using big data, with especially remotely sensed data for our project on the environmental impact of Konkan Railway. Thank you for your time, and thank you for giving us this opportunity to present our work. Thank you very much.
Thank you very much, Aniket. I want to open the floor in case there are any questions. So please feel free to enter in any questions you have for Yan Yan, Srija, or Aniket into the Q&A. I have some questions myself, so I'm going to get started with some questions. And as I do, please enter some questions of your own. Okay, so let's see, where should I start? Questions. One question, I guess, for all of the presenters has to do with the granularity of your data. So spatial granularity in terms of what's represented by a pixel. You know, it was a little bit different in each case. I think, Yan Yan, you were talking about the EVI index was 1 kilometer per pixel, and the SIF was 5 kilometers. And Aniket, you mentioned the granularity as well. There's also a time dimension of granularity. You know, how frequently are you having access from time snapshots? And from a research perspective, there's a question of, well, what is going to be sufficient in terms of the level of precision or granularity for your research question? And of course, there are also cost considerations. More granularity sometimes means you can't use the free sources of data. So I guess my question for all of you is, how did you decide what level of granularity would be needed for your analysis? And then maybe a side question to that is, given that some of the high granularity data is paid, did you have to decide that and figure that out in advance of submitting a research proposal to get funded? So maybe can you talk through some of the considerations related to granularity and the cost for accessing data sources? Maybe I'll let you volunteer to see who wants to go first on that one.
Okay, I can talk about it first because for safe data, the highest resolution data is 5 km. So we basically have no option. And for EVI data, 1 km is, we have open access of EVI at 1 km resolution, because this project is target watershed. So we think that resolution is good enough. And we already have a large sample size to help us identify the program impacts. So we didn't go through the even higher resolution, because in that case, you need to, the cost would be high. So it's basically the selection of granularity is based on the need of the project, also considers the cost of carrying over this project.
In our case, you know, we had to measure the impact after 1999. So, you know, post 1999, we have a lot of options in terms of, you know, to choose from. So we could have even gone for hyperspectral data if it was available. But in the pre-treatment year, so that was a problem. I mean, which pre-treatment year do we choose? And so early 90s, because the railway construction began somewhere in the mid 90s, if I'm not mistaken. And but if you go too back in time, then we get very coarse data. So we get data from either the LIS-1 sensor or from the Landsat MSS, multispectral scanner, which is about, I believe, 60 meters spatial resolution. Also, the number of classes that we could have been able to classify with successful accuracy would have reduced, and as it is, they're very less. So I think 1991, we chose 1990, 1991, that period, because at least we have medium resolution data, that's 30 meters from Landsat. And LIS 1, LIS 2 were available, but again, they were coarse resolution. So again, this, I mean, this is something that I'm still not able to completely figure out. So if you want to do historical studies, I mean, if you want to do a historical land cover change, the options really are limited in terms of what granularity of data you can, you can use. Now, at this point of time, because you have hyperspectral, you've got your wide sensors like your MODIS or your AVHRR, as well as, so that gives a more spectral resolution. So these are inversely related. The more number of classes you want, you will have to compromise on your spatial resolution, and vice versa. And the only way to bridge that gap is use hyperspectral data, which is not historically available. So really, for us for data on pre-treatment year, there was no other choice besides using Landsat 30-meter resolution data. It was the best option. So, and it's available free of charge. It's open source.
Yeah, thank you. So sounds like in both of your cases, the choice was clear, and you didn't have to do much analysis to figure out that that's the source that you needed prior to completing your research proposal and requesting the funding. So you knew I don't need to request the additional funds. Though Aniket, you did present the resource SAT costs. So I wonder about that. Is that something you knew in advance? Yes, I will need this. Or did that take some preliminary analysis and processing to figure out that you needed that at some point early in your research process?
one of the reasons to choose ResoSat over other satellites is that one is that it's so Landsat is still available, but the resolution is a little lesser because a LIS3 sensor was fitted by that time on IRS-1D. And the second is that we got it at an institutional discount price. So we got it at 50% of the price for commercial use. And the second is that because it's based in India, like we did get a few bad scenes that were sent to us, but we were immediately able to get them replaced through communication. So I think that was the main consideration, that in case we do get bad data, then can we get it replaced very quickly? And we had no prior experience with other space agencies on replacing bad data, so this was the natural choice.
Thank you. Okay, so we have a question. Thank you, Lorenette. Lorenette Gonzalez asked about the types of variables that are useful to gather or feasible to gather for using remote sensing. So we know that we're using sensors and satellites and drones. So these are variables that have to be observable from above. The question is, as presented, remote sensing can be used for evaluating environmental or infrastructure projects. Can remote sensing also be used for agricultural productivity projects like like coffee or coconut? Are there any examples of evaluations conducted on this using remote sensing? So I can share a little bit about that. I'll let you reply first. Whoever, this is to anyone, if you want to comment on remote sensing for agricultural productivity.
Yeah. Yeah, can I take that?
Yeah, go ahead.
Yeah, I believe it's being used a lot. One study that I have referred to is by Lobel on the agricultural productivity of wheat. So he has used modest data, and he's been able to compute the yield and also predict the yield of wheat and other crops. And he has done these studies for Africa as well as for the Indo-Gangetic plains. So that's one study that I have come across. It's by Lobel. I don't recollect all the entire the full name of the author, but yes.
Yeah, thank you for sharing that. And just to respond, yes, agricultural productivity is really an important application of remote sensing data. And various kinds of indices have been used to try to look at productivity of fields. And researchers actually appreciate remote sensing as an alternative to, say, crop cuts, because of the resource intensive nature of actually gathering that, and also the recall of farmers talking about their yield of various types of crops. So yes, big application for agricultural productivity, though there are variations depending on the type of crop. So if it's coconuts coming from coconut palms, maybe a little bit harder to observe that from above. Coffee, not as sure about that. Whereas other kinds of crops like wheat, it's much easier to see in an open field what's happening with the crop, if there's damage, if there's bare soil. So imagining a straight line above from the crop and what's going to be visible from that vantage point is a good clue. There's other research showing that deforestation is another important variable studied with remote sensing. But forest degradation is harder because you're having loss of vegetation, but you can't necessarily see all of the loss at the lower level because of tree cover. So it's harder, it's a little bit harder from that perspective. Let me stop there. Yan Yan.
I want to invite my co-author, Jiaming Wen, to respond to this question, because he and Yingzi had been working on this topic from another direction through SAFE instead of vegetation indexes.
Excellent. Yeah, please. I would love to learn more about this. So do we need to give microphone access?
Hello?
Yeah.
Yes, we can hear you.
Yeah, okay, great. Yeah, so our group actually working on satellite SAFE product, which has been used in this Yan Yan's project. And in the recent decade, SAFE has been evolved as a very good proxy for photosynthesis and for crop yield estimation. So there are a bunch of studies that is using SAFE to measure crop productivity and crop yield. And our group also did a lot of analysis for crop yield estimation for US Corn Belt and Ethiopia and India. Yeah, so I think does it answer the question? And what else?
Yeah, it would be helpful because SAFE is a very new series. So it would be helpful if you could explain the advantage of using SAFE versus vegetation indexes. Jiaming, could you explain that a little bit more?
Yeah, sure. So SAFE is actually quite different from the conventional vegetation index like NDVI or EVI, because those are purely grainness based. That is, those indices are measuring how green the plant is. But SAFE is a little bit different because SAFE is involved with the core mechanism of photosynthesis. And SAFE not only contains structural information, that is how much light is absorbed by the plant that is being used for photosynthesis, but also it contains the information from a perspective of physiology, like the light use efficiency, how the absorbed light is being used for photosynthesis. So that's why SAFE, a lot of studies have compared like SAFE the performance of using SAFE to make prediction for crop productivity versus NDVI, and we see a better performance using SAFE.
Great, thank you. Thank you so much. That's very helpful and fascinating to learn about, and also very exciting that there's always new advances. And then I guess that's a takeaway for everybody who's attending, is that the advances are happening very rapidly in this space. Measurement studies to validate different kinds of measures using remote sensing are coming out all the time. And as those measurement studies become available, that means that researchers who want to evaluate outcomes that can be measured using those indices can start to use them. So really, it's just a question of trying to keep up to date with the literature and the measurement studies, and keeping up with how people are making use of those, like this team. So I guess that's a segue into my next question, since I don't see any more coming in the Q&A here. And that relates to a question of construct validity. So how do you know you're measuring what you want to measure or what you think you're measuring? We're obviously constrained to some extent by what we can observe from remote sensing, whether it's EVI or SIF. In some cases, we're hoping, and we should find, that there are validation studies that would show, yes, in fact, when we do compare the spectral image or the visual, these pixels, the signature to a gold standard of something that was on the ground, we see that there is high correlation, and that we can predict with high accuracy the actual on the ground reality with the spectral image. So it's very helpful when there are validation studies showing that. But there also can be variations across geography or in different microenvironments. So the way that these signatures apply, I'm less familiar with SIF, so maybe it's less of an issue. But for EVI and some other uses of remote sensing, what looks like one thing in one part of the world or in one region might actually not signify that same thing or to the same extent somewhere else. And so it raises this question of, well, can I use this remote sensing data source and just conclude or infer that this is the variable, I'm measuring it accurately? Or do you need to do additional ground truthing? And Aniket was mentioning this, ground truthing costs can be high. So I guess the question to the panelists is about ground truthing and additional validation of your measure. What are the things that you're keeping in mind to decide when you feel confident enough, or what makes you feel confident enough to use a remotely sensed source for your variable of interest?
Can I address this question first? I think it's in our case, we use two complementary measures, SAFE and EVI, to do robustness check. And also we restricted our period to be the main crop season, and also restricted the pixel to be crop land. And we used to crop our range land because the land cover also related to, can complicated, can mess up affect the index, right? So we use two crop masks. So it did a lot. We use different drought indicators, different cutoff, and different ways to generate the drought indicators. So it's just like, I feel like the geographic data, geospatial data is just like household data. There's measurement errors, different type of measurement errors. But if we try data from different sources, different methods, and also for the models, from econometric models, we use different specifications. All of the results are very robust, pointing to the same results. That really improve our confidence of our study. Also, on the other hand, it would be very useful to complement this study using the survey data. And that is part of this whole project. We actually also look at LSMS data and the DHS data merged with the program locations. And we also found some impact on household well-being, positive impacts. And this also help us to be confident of our results. And in terms of ground truthing, I think Jiaming can address that question better than me. Jiaming, could you address about the series EVI and the SAFE series used about the ground truthing, how that increase our confidence of doing that? Yes,
sure. So yeah, that's a really great question. I think we should always be cautious about what we observed from remote sensing satellites. And indeed, I think, so let's first talk about EVI. I think EVI is a well-established metrics to evaluate the vegetation status starting from 1970s. And currently in the past of several decades, people have already used that for vegetation status evaluation for a really long time. And the SAFE is kind of new and starting from the recent decade. And we We also start to set up towers across the world and try to validate our safety retrievals from the satellite, make sure we are measuring, we are observing what we want to measure. And I also agree with Yan Yan. I think the survey data is absolutely necessary. And I think the survey data and the satellite data are always complementary, and we shouldn't use satellite data to replace survey data, because survey data can still provide reliable underestimate and to validate our results with remote sensing data. That's all.
Thank you so much. Very helpful. I fear we're running short of time. We have just 3 minutes left. I'm wondering, I think, Aniket, you were preparing to reply. Will you be able to do it within 1 minute?
Yeah, so the concern is very real as far as, but you know, fortunately we have metrics like kappa statistics that help determine how close is your classified output to the actual data on the ground. But the problem again here is with the reference images, and ground routing is the best. There's no substitute to ground routing. But the problem is, how do you do it? You can't possibly do it for historical data. So, but maybe through integration of techniques like, you know, a PRA, a participant rural appraisal, etc., which can be used to corroborate what historical data tells you, or data from surveys, from land surveys, etc. That could be used. But and this concern is, about the indices. This is especially true with global land cover data sets, because a certain range in a temperate region would signify, first of all, it would map to different kinds of vegetation cover as compared to in a tropical region for the same index. So we don't have a proper classification matrix of the vegetation index and to what kind of vegetation it actually maps. So that, I think, is a big challenge.
Thank you so much. Okay, so final word. I just want to wrap up, sort of recap some of the things that we heard and learned from the session. 4 key themes came out: value proposition. Why is this important? Why is it useful to have remote sensing and impact evaluation? In both cases, really the study would not have been possible without using remote sensing. In the Ethiopia example, Yan Yan explained that they would not have been able to, there was no household survey as a baseline. Just it wasn't there. There wasn't enough scale in household surveys to make that feasible. In India, Aniket and Srija were talking about it, using the remote sensing data source was the only way to get sufficiently recent and frequent data on land use and other variables. And in some cases, there were measurement issues with the existing administrative data on the ground. The remote sensing data for the Ethiopia study also was very helpful to test for the parallel trends assumption in the difference design. Wasn't the case in Ethiopia, but that's a very valuable contribution if you're familiar with that design. So overall, the applications added feasibility, cost effectiveness, scale, and accuracy in these cases. Key process details that the presenters highlighted included identifying the specific data needed to measure the outcome variables, and then thinking about what's the identification strategy. So this is the bread and butter of impact evaluation in general. But the additional importance of considering the unit of analysis and the unit of granularity dependent upon the spatial resolution of a dependent variable. More intensive data processing steps to consider: image correction, georeferencing, merging, lots to think through there and to make sure you get right. That has to be done very carefully. You saw the detailed flow chart that Aniket and Srija were sharing. And there's a critical role of machine learning with supervised classification to help get this done as well. Additional steps related to validating the work for these reasons. Some of the challenges, there were technical challenges, some of which I just mentioned, and capacity challenges, including the need to have an interdisciplinary research team, and in some cases, the difficulty or the costs to actually do ground truthing over a large area, which we were just talking about. From a resource perspective, again, interdisciplinary teams critical for this. The need to have high capacity computational support, whether that's your actual machinery, the processors in a high-end computer with robust memory, or access to cloud services like Amazon Web Services to analyze big data, and the financial costs. In some cases, the cost of proprietary remote sensing software, travel costs for ground truthing, donor support to fund the work in any case. But all in all, key takeaways, high value, and this is getting easier, more accessible, more useful, and more widely used in evaluation all the time. So there's a lot to learn, but there's also a very active and enthusiastic community working on remote sensing and geospatial analysis to make it more accessible. So there's a lot there, and one place where you can access some resources and a growing set of tutorials is on the Geo4Dev website. It's www.geo4.dev/training. There's a training page, and there are more resources coming up on that all the time. Many other sources as well. So anyway, thank you all very much. Thank you to the panelists, Aniket, Yan Yan, Srija. Excellent session. Thank you to the participants. And I believe you will receive a survey after this asking about your reaction. So please do fill that out. Thanks very much.
Thank you.
Hi, thank you.
Thank you.
Thank you so much.